general data regarding because as we talk the so much of the powder production with respect to additive when you comparing with the subtractive manufacturing process, we need to know how much the greenhouse gas effect is going to cause for environmental effects, what is the cumulative energy and demand is required, how much electricity we are using for our additive manufacturing machines productions and additional and as well as for the gas and as well as for the powder productions and all. See, you are all aware that just the general data, one of the review article has given this cumulative energy data, because this cumulative energy data is required when we are thinking to manufacture the machines of additive machines or the powders or as well as the gas productions, right. This cumulative energy data requires like lot of environmental effect. What are those environmental effects? One is with respect to the production of machines, because even though we produce the machines whether conventional or additives, there is a environmental effect. And other one is how we are making this, the usage of the machine, the generation of the electricity, because to run the machines we need to have the electricity. And apart from this, the production of the machines, production of the powders and as well as the production of the gas and as well as production of your the additional post processing equipments which is required for AM processes. This will all relate to us the cumulative energy development or the demand, how much energy is required for our powder production or for the machine productions. That is what majorly important aspects in the when we talk about the sustainability of our additive manufacturing aspects. As majorly we are aware that like we think that this is most sustainable manufacturing processes, but as Professor Joshi has already told, we need to think of in what aspects the additive manufacturing machines are sustainable, because some of the data they are given from some literature articles. I will just tell you, in the entire world only one manufacturers, that is the Renisha AM250, you are aware of that, the AM machine manufacturers, Renisha, Concept Laser, SLM Solutions and as well as the Beam. There are so many manufacturers are there, EOS Solutions, but Renisha has given only the data how much cumulative energy demand is required for the machine manufacturing. They had given us almost 124 gigajoule for the primary is required for, that is for the primary manufacturing machine 124 gigajoule, that is for the machine manufacturing, and almost 12 gigajoule is required for your auxiliaries. The auxiliaries means it is such as chillers are required. All our AM machines we need to have the chillers, because it has to be continuously cooling has to be takes place for our AM machines. Means that much amount of huge energy is required for manufacturing of AM machines and as well as for the chillers and all. But there was no other manufacturers like with respect to SLM Solutions or other additive manufacturing machines, nobody has given the data how much energy we are utilizing for manufacturing the machines and as well as for the auxiliary equipments and all. But this is going to give us lot of importance, because any part you want to print, how much energy consumption will takes place, because as we know that this is the most complex parts we can easily fabricate it, easily build it, even which is not possible by conventional manufacturing process. That is the major beauty or the requirement for our additive manufacturing process. But do you know that how much energy is required to print that part? Take for one example of your the additive manufacturing of the impeller part of aluminum. If I want to print aluminum impeller part, how much energy is required? Given the data, one of the authors, the for aluminum to make one impeller, they require almost of the 6 to 60% of the cumulative energy demand is required for the part. That depending on the size of the part, the cumulative energy means the size is again constant here, because that is again depending on the build volume of your machines, from smaller machine to the bigger machines. Again the energy demand is changing with respect to the build volume, because in the worldwide entirely we are having from almost 10 liters to 130 liters of maximum build volume we are having in the world in the additive manufacturing machines. But that is also having lot of constraints in the build volume aspects. To manufacture one like impeller, we need that much of 60% of the cumulative energy demand. But if you think of that, this is for the part manufacturing. Then again if you think of the powder manufacturing, again you think of the argon manufacturing, because these are all the two major feedstock for our additive manufacturing. One is powder, one is argon. These two are the major the feedstock materials, as Professor Joshi also told you, powder and as well as wire. But related to my talk, only I am giving you the important aspects of the powders and the gas, because gas is also a feedstock, because we need to purge the gas for the entire or PBF systems, or in the DED systems we need to protect over the beads. That is what the protecting gas we are using, or even the carrier gas for powder flow and all, argon for our titanium or more reactive materials and all, and for your stainless steel or ferrous based materials we use the nitrogen and all, and even some cases we use for helium as a gas for protecting media. That is what we need to think of. Even for the powder productions, people will say the global average cumulative energy demand for nitrogen almost 6 megajoule per kg. If you want to generate 1 kg of the nitrogen gases, we need required almost 6 megajoule. That much of energy is required. Then for argon, they have told almost 38.6 megajoule per kg. Means if you want to generate that much of the argon gas, we need to spend that much of 38.6 megajoule energy. And if you want to make some kind of a powders, how you are thinking? Powder manufacturing, is it easier to manufacture? What are the kinds of manufacturing of the powders? Even today morning he has discussed how do we manufacture the powders. Like if you know that the powder manufacturing, most people are working with stainless steels, titanium, nickel based superalloys, and as recently majorly working on aluminum alloys and all, especially for additive manufacturing aspects. But for powder manufacturing, how much cumulative energy is required? Especially they are given in the literature data, because we need to use argon gas, the argon consumption almost 5500 liters per kg to manufacture the parts and all, to use for our atomizing the powders. If I want to manufacture 1 kg of titanium powders, I need to spend almost 5500 liters of the argon gas. Yield is going to be affect our environmental aspects, definitely. But when you comparing the conventional scenario, how much feasible, in what sense we need to think of which is going to be feasible aspects. And if you think, for example, the steel, they are given lot of different data, 18 megajoules, from 18 to 50 megajoules per kg of the steel powder productions for atomization aspects. And for titanium, I told they are using 361 megajoules to 582 megajoules, 361 megajoules to 581 megajoules per kg of your titanium powder manufacturing. That much energy is required, and for per kg of your powders, they require almost 5500 liters of the argon gas is required. And similarly for nickel, they are having almost 114 megajoule per the gas, the energy is required for nickel based alloys. Means this is just the data I am giving you, just to understand how we are to think of in what way the sustainability aspects, because the only aspect the powder productions and how we are making use of this powder production for additive manufacturing aspects. Do you really comparing with the conventional aspects? Yes, even conventional machining aspect, how much energy consumption for machining and what are all the environmental problems we are going to attain, and what is the how the raw materials we are produced for manufacturing with respect to conventional scenarios. Then coming to these, the requirement of the powders are with respect to the cumulative energy demand, then how do we manufacture the powders? Are we in the today's scenario, because this manufacturing especially for the metal started almost 20 years back onwards. Since 20 years, are we really using the powders manufacturing from the ores? Because any raw materials you want to manufacture or produce or the extract, it has to be extracted from the ores. Are we really till today we are using the powders are manufactured from the ores? Then how we have to make use sustainable aspects? Let us discuss on those things aspect. This is the content I am going to tell you about this the overall lecture for the 2 hours. What is the aim trend? What are all the metal powders we are using? And we are discussing what are the powder productions, majorly with respect to the scenario of atomization, because he has given the glimpse of powder manufacturing aspect today morning. We will go more in deep how the powder manufacturing or production is taking place, and as well as how do we characterize, because we know that the sphericity is important, flowability is important, but will the non-flowable powder particles are we using or not? How much extent we can use non-flowable powder particles? In what additive manufacturing we can use such kind of the non-flowable powder particles? And also the remanufacturing of the powders. How do we use reuse of your powder particles? And then what is the sustainable feedstock sources for your powder manufacturing? And as well as the effective powder management. These things we can discuss in this. Okay. If you see the AM market trend, since from 2023 to 2028, this is the projected data from the Oilers Association. If you see the cumulative growth rate, almost 16.1% the growth rate is the prediction, because this data has predicted from since last 5 years data how the additive manufacturing people are using with respect to all the scenarios. And if you see the AM market trend in terms of the powders only, this is with respect to the global market of the metal additive manufacturing process, and this is with respect to only with respect to the metal powders. If you see the scenario, the Inconel and stainless steel almost 40% of the powder growth is going to be taking place. In all over the metal additive manufacturing, we are mostly using stainless steel and Inconel, and now the development is taking place on the titanium, because of lot of qualifying components are using in our the aerospace applications and as well as medical applications. People are trying to use the 15 more than requirement for the additive manufactured parts in the aerospace and as well as for the medical applications. But if you see this research data has shown lot of the powder cost will be the highest continuous expenses through the life of AM machines. As we know, for one machines additive manufacturing machine cost, we know that almost $20,000. The simple small machines we need to get 1.5 to 2 crore of machines is required. That is depending on the build volume. If you want to have a 10 liters of build volume, you can go get it from that the 1.5 crores. But if you want to go the build volume size increases and as well as the multiple lasers if you want, then it will cost around 15 to 20 crores big machines capacity is required. Then will that really required? Only the machine is there, that much big volume machine, can you directly use that part manufacturing for the applications, real time applications, or directly I can use that near net shape manufactured part into the ready to use applications? No, because we need to think of how effectively we have to utilize AM parts. Again we need to use post processing, right, and the post processing cost also will add up on the manufacturing cost of the part. And powder productions, are we using original powders? are we using reused powders? That will all come across into a part manufacturing cost. Then you need to think of whether that part is quality is consistent, because lot of challenges are in AM machines, AM part manufacturing. If you manufacture part from EOS solutions, or if you manufacture part from SLM solutions or from the Renisha, the part quality is different, because we are not getting the repeatability from different manufacturers to different manufacturers. Even though the process mechanism is same, they are using same concept of mechanisms, but our part quality is different. Then what is the challenges we are facing? Why do we are having this, the less in this repeatability aspects? Are that parts are qualifiable or not? Then is this mainly because of the powder feedstock? No, machines are 100% right. This is mainly because of the powders. Do you maintain the powders are used for all the machines are same? Is it from the same batch we are using the powders, or we are using from the different batch of the productions? Because even if you are using the same machines, if you use a one lot of powder and then if you use a second lot of powders, are we matching the same properties what we are used for the batch 1 or batch 2? That is also challenging issues are there with our AM machines. Then how to address all these aspects? And if you see that the global scenario for the powder market manufacturers, you might be aware that overall the powder manufacturers, the Hoganas, Praxair, and as well as the Sandvik, and even the 6K solutions, 6K additive solutions, and even in India, Indomim, and as well as some of the small scale companies, they have Matrix Nanos and all. These are all the global leaders for manufacturing the powders. Then if you see this, the growth rate with respect to the precious metals, more than 12% is growing, and with respect to the platinum materials 11.5%, and with respect to aerospace, that is on the super based alloys or on the titanium based alloys, it is 22%. And with respect to the titanium, it is almost nearly 30% growth rate is taking place since from 2021 to 2020. This is what the rate of the powder requirement in the additive manufacturing scenarios. Then how do we manage all these powder productions? Yes, we know powders are required majorly for the additive manufacturing process, especially for the powder bed fusion and as well as for the laser DD process. Apart from those two major metal powders, binder jet is also now moving more on to the powders, because these three major processes, if you see, this is the pie chart. If you understand here, we are using most of the powders for this material jetting, material wet polymerization, binder jetting, hybrid binder jetting, mold slurry deposition, metal laser sintering, or electron beam powder bed fusion, or maybe the laser beam powder bed fusion, laser electron beam, powder laser DD deposition, and as well as for the cold spray technologies. For all these AM technologies, we need the powders. Then if you see the growth rate 8% in 2024 to 36, and as well as what are all the growth drivers, that is what the surgical increase in the demand of automotive industries and as well as for the aerospace industries, the market, the metal powders growth is taking place. That is based on this region wise with respect to the Asia and as well as with respect to the North America, we are having this much of the growth rate. That is also with respect to the ferrous and as well as non-ferrous materials. Majorly we are growing with more on ferrous based materials with respect to this. As I told you, the most leading manufacturers for these powders are Hoganas, GKN Aerospace, and as well as the Sandvik, and as well as American Cement Corporations and the Carpenter. These are all the leading manufacturers for our powders for the additive manufacturing. Then even today's morning professor told we need to choose from which manufacturers we need to buy the powders, because if you buy the machines from 3D systems will tell you need to buy the powders from 3D systems only. Yes, but can't we use any other powders for the 3D systems machines? They are telling whatever the process parameters we are given to 3D systems for printing the stainless steel materials will not work if you buy the powders from other systems. Is that a real scenario? No. Because we need to think of how the solidification is taking place, how your laser and powder interaction is taking place, and what is the process conditions we are using for the printing aspects and all. Right, if you see here, hence we need to understand the quality of powders which we are using for our IT manufacturing process, who is the supplier, and whether it is in original condition or in the reused conditions. In majority scenario, in the Indian scenario, what we are buying? We are buying the powders even sometimes from the local manufacturers. Like you might be, as I told, the Indomim are most leading manufacturers for the injection molding parts and all. They are also producing the powders especially for the powder metallurgy aspects, because as powder manufacturers can only segregate the powders which is required for coating, which is required for powder metallurgy, which is required for IT manufacturing. They cannot go only for IT manufacturing aspects. Even some of the Chinese powders, Indian scenario we are getting, but will that the original powders, or it is a reused powder? Again they are using spheroidization techniques or atomization techniques to make it spherical, make it to improve the flowable properties and sending into the Indian scenarios. From these powders, are we getting a good quality of the components? Then whom we have to blame? Whether the powders or whether we have to blame the machine. Then we need to have the challenging issues, repeatability and as well as the mechanical properties what we are getting after printing the parts. Is it because of the powder defect or because of the machine variations? That is what we need to understand, whether the powder is what quality it is. And then that is the quite challenging for any beginners, any new additive manufacturing machine manufacturers as the researchers. That is the major challenges. How do we decide the powders from which suppliers we have to buy, whether from the US solutions or from the Praxair or Oganas or maybe Carpenter, Sandvik, ATI or Tecna. These are all the worldwide suppliers. Everybody will supply the powders, but they are not meant only for our IT manufacturing. They are the leading powder manufacturers for thermospray coating, powder metallurgy as well as for IT manufacturing. They are just only segregating the powders which is different processes, right. Then are that powders are validated? Are we using that validated powders? Is it suitable for the use in the IT manufacturing process? Then how do we choose, how do we validate these powders for IT manufacturing process? And that wish list, the validated powders can de-risk of procuring the powder for AM. It does limit the under the signal the sources of the suppliers, inhibit the development of in-house expertise. Means anyone cannot buy the powder from the market. You need to understand how powders are manufactured and what powders we are using for. You need to think of which is the powders are suitable for IT manufacturing process. Then majorly then we can think of atomized powders. Then how automation takes place, how do we understand automation process? Then what are the types of automation process are there? The common method, the cheapest production method is milling. That is what the mechanical process, the mechanical methods. But these mechanical powders we cannot able to use for our IT manufacturing process. That is what mechanical ball milling or tumbler milling or different kinds of mechanical attritions. These kind of process we are using for mechanical powder productions and all. But will that powder suitable for IT manufacturing? No. Because when we use in the powder bed, we need to think of highest packing density, highest compressibility ratio and as well as packing density in the powder bed. But in the case of the LDD process, we need to think of how the powder flow takes place from hopper to the your deposition nozzle head. Will that 8% if you are giving 8 gram per minute or 10 gram minute, will that 8 gram per minute is exiting in your nozzle? that is depends upon flowability of your powder particles. If flowability is not good, it is going to stuck inside your the pipe of your from hopper to your nozzle. That is what the flowability is important aspect in our powders. Then if you see, as I told, the powder manufacturing process for our AM is atomization. That is what the physical method we are using, powder atomization. Again in that atomization techniques, we have gas atomization, we have plasma automation, we have plasma rotating electrode automation process. These process methods will give us the powders are manufactured by automation. But when you think of this the process of atomization, we have this the many methods, that is what in the automation techniques, the gas, water and as well as the plasma automation. Again in that plasma we are having plasma rotating electrode automation and then spin off methods, there are different techniques out there. But if you see here in the gas automation, whether we are using argon or whether we are using nitrogen, and in the water we are using water atomization, which is followed by the oxide reduction under hydrogen atmospheric conditions and all. But when you use these kind of techniques, what properties are widely depending on the automation techniques and how the manufacturing conditions are takes place. Means if you think of which powders we need to select for our AM, this is what the process conditions for automation, and then the importance of the powders, why the powders are important in our manufacturing scenario, and routes of powder productions and the powder recycling. Means how powders are important in manufacturing. If powder quality is poor, then whatever you play in your process conditions in manufacturing the part and all, ultimately you will end up with a poor quality of the part and all. That is why the important is the powders. And then we need to understand what is the roots of this powder productions, how it is manufactured. Is it manufactured directly from the ore or from the ingots or from the reused powders or maybe from the scrap. That is what we need to see, the roots of the powder productions and then powder recycling. If you see the importance means how critically influences on the final component properties, because we know that in the DED or in the PVF systems we have discrete amount of the powder feeding in the hopper, because in the PVF powders will be dispersed on the build platform area, but in the DED systems powders are feeding into the feedstock to purge into the coaxial nozzle or bidirectional nozzle, whatever the nozzle arrangements will be there, that will be fall on the focal point, it interacts with your laser, then melt pool will form in the flight and then deposit a bead. But in the powder bed, your compacted powder will be there by the doctor's blade or by the roller, then you will be having so much of packing factors. We expect one packing factor, but that not going to be a one factor. Depending on that factors ratio, we are going to melting and solidification is taking place. Apart from the process conditions, the powder quality is also a important aspect. Is that powders are homogeneous distribution is taking place in the build platform area. For that we need to have the Gaussian distribution of the powder particles. That is what important in the Gaussian distributions. If you go with too much of powder pooled in one area, what will happen? Definitely the laser will interact with that one pooled powder particles and it won't melt properly that pooled powder particles. In some area, if your powder is not dispersed properly, then it will melt, it will create so much of the empty spaces. That is what the pores are going to create. This is the problem will be there if you are not having homogeneous distribution of the powder particles in the build platform area. That is we need to understand the importance. That is what the powder performance in AM, how much layer spreading, hopper dosing or the bulk packing depending on the properties, and as well as the build efficiency and the unused powders and the cost factors. Means the build efficiency means is that the actual component volume is significantly less than the total powder spread, because if you take 100 by 100 mm of your build area, we are spreading entire build area of our powder particles, but will that we are using entire volume of a build area for the manufacturing the part? That is dependent on the what part we have designed and how much area of melting is taking place. We cannot use 100% of the build area, that is also with other constraints and the build defects what we are failed in the printing scenarios and all. But then unused powder, for example, if you build 100 by 100, then if I print only a 10 mm part in that build area, how much part we are losing, how much powder particles we are losing. That is what the large amount of the powders remains unused in the build after the printing. And the cost factor, given that highest cost of the metal powders, effective recovery and as well as reuse of unused powder is essential, because it should be essential, because we cannot buy every time new powders for printing the part and qualifying it, because that will lead to a lot of cost of manufacturing in the part. Then how do we have to manage, how much times we have to use this reused powder for printing of parts and all. Directly can we use this unused powder for the printing? We cannot use, because it may change the surface properties because of the oxidation, or it may change because of the thermal properties. There is a slight heat absorption taking place by the surrounding media, or reacting with the reaction of the gases during the melting aspects, and also maybe agglomeration in the surrounded powder particles, or some satellites are sticking onto the surrounded powder particles because of the multiple ejections from the solidification and melting. With all these criteria, we need to think of how to use unused powder particles in the build platform. Again we have to receive, and then we can think of how much quantity of powders we have to mix with your original powder particles. I have original powder particles 60%, and then 40% of the reused, that is what the sieved powders I can able to mix with the original powders. Then what is the cost factor? That is all depending on how much efficiently we are recovering and reusing our powder parts. And if you see the roots, that is from directly from the ore, we are extracting and then forming the ingots, and that ingots are used for our automation process, either the gas automation or water automation or centrifugal automation process, then to make the powders directly from the ore, right. And then if any hydrogenation or dehydrogenation, that is generally using for our titanium powder particles and all, we are reacting with that process is the titanium oxide or titanium hydride, then we can extract directly titanium powder from the titanium hydrides, that is what the hydration and dehydration. This is what the stages of the powder production from the ore. But are we really following these kind of the process for the till today? That is what we need to understand, how much efficiently we are using these powder productions. And if you see this, as I told, atomization, then how this automation process works for the powder productions. In these automations, any material which can be weldable, which can be possible to melt, which can be able to make the powders and all. That is what the breakup of liquid into a smaller droplets, it is called the atomization, typically into a range of 150 micron, means less than 150 microns, whatever the particles you are producing from the billets or from the ingots, that is called the powder particles by the automation process, right. But that how do we process this automation? What is the mechanism of this automation? You see this the mechanism of automation, stage 1, stage 2 and as well as the stage 3 and stage 4. In the automation chamber, if you see, this is the big automation chamber, either vacuum or argon automation chamber. We are purging our molten pool materials or the ingot materials, and that it will drop down and we are impacting that with a high velocity. that we are disturbing that molten pool with a very, very high velocity of the water or by the gas. With that, what will happen? It will create a sinusoidal wave in that molten pool. That is what in the stage 1, the wave is going to create the sheet of molten pool, that is in the stage 1. Then that powders are going to, as a fragments or the ligaments are going to form in the stage 2. In the stage 2, it will break that sinusoidal wave into a ligaments, and then that ligaments further it will break down into a droplets. That droplets are going to create as a, in the stage 4 in the automations, as a small particles. That small particles are collected, will that have a size reductions by the limited viscosity or temperature or the acceleration forces. With these, the stages of mechanism of powder particles are going to take place in the automation process, either water or either gas automation process, right. If you see, this is what the big industrial automation in the argon going to take place. And if you see the process of water automation, as I told, all the mechanism is same. We are purging our liquid molten materials into the automation chamber. This is the complete automation chamber. In the stage 1, with high impact velocity of your water droplets, we are impinging with very, very high velocity to create the sinusoidal wave that will break down again into the ligaments and as well as the particles of the powders. And how do we control this? Can we able to control? How we can able to control the powder particles, either in the gas automation or in the water automation? In the water automation, we are impinging with very high velocity based on this, the nozzles of the water inlets. But in the gas automation, we are purging with respect to a high amount of the gas in this nozzle area. And all these we can able to produce, then when to use this water automation and when to use this gas automation process. Then what is the problems we are facing when we use water automation and as well as gas automation process? If you see here in the gas automation process, we can melt and we can feed the powders less than 120 kg per minute, and we are going to get the powder particles in the range of, I think 100 to 500 micron size. But when we melt this, how do we control the powder particles? What is the rate of impingement, whether your gas or whether your water, in what rate we are impinging into that molten pool, and as well as the velocity, and what is your orifice angle, that is how much water inclination is falling onto your molten pool. With this, we can able to control the formation of your diametrical of the powder particles. That is what, if you see the two differences here, the D50 is 200 micron and D50 is 29 microns. The major changes is here only the gas impingement, how the gas impingement takes place onto this molten pool and all. That is what we can able to produce. If you see in this scenario, we are getting less than 45 micron, only 5%. But in this scenario, we are getting more than 70% of the 45 micron powder particles we can able to get. That is by altering the impinging angle and as well as the velocity. This is what we can able to easily control with these scenarios, right. And if you see in the recent developments were taken place by the 6K additive solutions, that is what vacuum induction automation technology that meets especially for our the titanium powder manufacturing process. Because in the titanium we are generally using for the argon, because titanium is highly oxidizing materials, it will quickly create the titanium oxides. Because of to protect this oxidation formation, we have to use either the vacuum chamber or we have to use a argon atmosphere conditions, right. And how do we control? As I told, if you see with that velocity, we can able to control the particle diameters. Means if you see this, the geometric constant with respect to the acceleration gravity and how much amount of the injection of the pressure onto the molten pool, and as well as the pressure onto the atomization gas, and as well as your density of the liquid molten materials. With that we can able to control the ligament forming into a spherical droplets. With these we can able to break and control the formation of the powder particle diameters, right. And how the evolution of the microstructures. Okay, the powder particles are breaked into ligaments and then droplets. In our additive manufacturing process, we are going to get columnar dendritic structures, but will that follow the powder particles? Why we are having these kind of the dendritic structures? What is the major scenarios with respect to this? Because of the rapid solidification. Means when rapidly solidifies these powder particles, it will create that the crystallographic directions are growing towards solidification in all the directions. With that, if you see that that is depending on the lambda, that is the dendritic arm spacing which is equal to the k T to the power of n with respect to the material constant and with respect to the cooling rate, and n is the constant with respect to the materials. Means if you understand how the dendritic arm spacing, whether the primary or secondary dendritic arm spacing is going to form, which can able to correlate how the solidification is taking place, what kind of the powder particles or microstructures we are going to get it in our additive manufactured powders and all. This is mainly because of the rapid solidification is taking place, means the freezing of your solid liquid interface is more enriched with your the liquid and solidification growth also. And if you see the different morphology of your powder particles, if you see the water atomized, chemically induced, and as well as plasma atomized, mechanically allied. What differences we are observing here comparing with your gas atomized powder particles? See, as I told, water atomized you are majorly using for the ferrous based powder particles, because it is not much oxidative, directly it can use, not much oxidation is taking place. That is what we are using water atomization for the ferrous based powder particles and all. But the powder particles which are more reactive to the atmospheric conditions, we need to go with the gas atomization or plasma atomization process. And also another scenario, if you see here, water atomization powder particles are not highly spherical. Non-spherical powder particles also we can be able to get it, because this is depending on the solidifications. In the water atomization, rapid quenching is taking place comparing with the plasma atomization process. The rate of cooling is different in the gas atomization as well as in the water atomization. Because of that, you are going to have some kind of irregular powder particles also going to get it solidified. And in the chemical reduced process, that is like a just spongy like structures, we are going to get it in the chemically produced powder particles. By the chemical reactions, we can able to extract the from ore to the powder particles. Those powder particles are not like a sphericity of the shapes. Then in the plasma atomization, if you compare with this gas atomized and the plasma atomized are more spherical powder particles, because in the plasma atomization we are using a plasma channel to melt our the filament of a wire, the ingots, and then solidification is taking place by your argon gas. We are not pouring the molten pool into the atomization chamber, with controlled velocity of the feeding of your feedstock materials, and then with the help of this plasma we can able to control rate of solidification and the formation of the sphericity in the plasma atomization. That is why we are getting a very good spherical powder particles. This is the powder particles are much suitable for our additive manufacturing process, but we cannot able to afford this much highly spherical powder particles because of the cost of manufacturing. That is the thing, we are using this gas atomized powder particles and as well as water atomized powder particles depending on the requirement aspects. Either simple parts which are not highly required for your aerospace applications, then no need to worry with your hot atomized powder particle. Yes, it will definitely flowable and it could have also the compaction ratios and also the packing factors. The packing factors mainly by the distribution of your powder particles. That is what we are using for DED process 45 to 110 or 45 to 90, and for PBF we can use 5 to 45 or 15 to 45. That is what the distribution of the powder particles we are using. Based on this distribution we are having a packing factors. Then if you see the mechanically allied powder particles, that is by the mechanical crushing, ball milling, attrition, we are having these kind of very irregular powder particles. These irregular particles are suitable for additive manufacturing? It is not suitable, but we can make use of these powder particles also by our laser direct energy deposition process. But these kind of powder particles are not suitable for PBF process, but we can use these powder particles for the trial testing to qualify the powder particles or qualifying melting and solidification of the aspects. For developing some kind of new alloys or new ceramic powder particles or new metal matrix composite powders and all, in such scenarios we can use mechanically allied powder particles can be used for your qualifying aspects and all. That is how we can make use of the powders with respect to the different manufacturing scenarios. And if you see the, as I told, the solidification and microstructure, how you are evolving your structure in your powder particles. That is, if you one nuclei will start to grow at random locations, like that individual powder particles, multiple nuclei will be there. That multiple nuclei will start to grow in random directions, that is going to create your dendrites in all the directions. If you see these kind of the in a one single powder particles, we can expect these kind of the solidified dendritic microstructure in your powders. But all these powder particles, how do we understand, how do we characterize this? These are all the microstructures of your powder particles, the morphology and the microstructures. But these dendritic corner spacing can be controlled by your solidification rating. That is what I told you here, the lambda is equal to K2 to the power of n, that is dendritic corner spacing is depending upon the solidification rates. If you see the copper alloys or the austenitic stainless steel or for the aluminum alloys, the dendritic corner spacing is different with respect to the solidification rates. With that we can able to control our the solidification rates to get the different kinds of the dendritic corner spacings and all. Okay. And regarding that plasma dimension, I told we are getting very spherical powder particles. Why do we get that spherical powder particles? Because here we are feeding the filament in the form of a spool of a wire, and with that plasma torch we can able to melt with a controlled amount of the molten pool materials, and then we can able to purge into a high amount of the argon gas to get the required particle sizes and all. That is what possible in our automation chamber. But the cost of manufacturing with respect to this plasma automation is going to be very high, because we need to maintain the plasma channel and as well as complete automation chamber. Especially these plasma automizers we are using for titanium powder particles, that will be very low yielding capacity. Because do you think that to get 1 kg of titanium powders, how much tons of metals we need to melt? Because we wanted to get 1 kg of powders, for PVF powders at least we need to have 5 kg of powder particles to build 100 by 100 volume for maximum of 10 mm thickness. To produce 1 kg of powders, hardly we have to melt 100 kg of molten materials, because we are not going to get highly spherical powder particles, irregular particles, nanoparticles, less than 5 micron, greater than 45 microns, all this has to be segregated. Only we are using in the range of 5 to 45 only for our PVF process. Then to produce only 1 kg of powder, that much quantity of powders material, molten metals we have to add, that is what you are having a very low yielding. It is only hardly 5 to 6% of the entire amount of materials yielding into a small amount of powder particles. That is what high powder cost and the limited capacity. That is what in the plasma automation, it is having a high powder cost and as well as limited capacity. And if you see, this is what the advanced titanium automation was developed by the 6K additive solutions and all. This is what the ingot in the complete chamber liquid metal, and it will melt and it will form as a supersonic gas structures, and then pulsating it is going to create as a ligaments, and that ligaments going to form as a droplets, and then that droplets will solidify, and in the container it is going to be as a powder particles. Then it will be sorted by our different kind of sievings and all with the different types of meshes and all. This is what the recent development by the 6K additive solutions. If you see, this is the like how much in the world the titanium atomizers will be there. That is a very big machines, even it will be more than industry big machines will be there. It will, because we cannot produce simple 5 kg or 10 kg of powders in one lot. At least they are going to produce in terms of 5 tons in the one automation techniques. That is why the cost of manufacturing is very high in this automation techniques. And the hydrate and dehydration techniques, this is another kind of powder manufacturing. That is what especially we are using for the titanium powder manufacturing. If you see, titanium is reacting with chloride, initially it will be in a titanium chloride, then we are dissociating chloride separation by the sodium reduction. With that sodium reductions, it is going to form as a sodium chloride, then you are ultimately end up with a titanium. That is going to be dried with your atmospheric conditions to get this titanium. This is what one of the hydride and the dehydration techniques which is majorly used for the pure titanium powder productions and all. Okay. We will stop this, and further we will continue with respect to the where manufacturing usage, how do we characterize, and then how we can think of the sustainability aspects in our additive manufacturing with respect to industry scenarios and all. Okay. We will have a break of some 5-10 minutes, then we will continue back. Okay. Powder manufacturing and as well as its use. Like we know what are all the manufacturing methods for the powders. Are we really using for all the powder manufacturing methods for the additive manufacturing? No. But if you see, in water automation, we are getting in the range of 0 to 500 microns. We can get in one water automation techniques that much range of the powder particle sizes. What will be the advantage for this water automation? We are having a high throughput, range of particle sizes, and it will require only a feedstock in the ingot form. We are using a feedstock in the ingot form. But what is the disadvantage? It may be contaminated with moisture because of the water atomization, and another is it is also a irregular powder particle distributions we are going to get it, and that the particle size distributions will containing have a satellites. That is what we will be having more amount of the satellite powder particles are there, irregular powder particles, and as well as satellites will be there in the water automation. That is the major disadvantage for our water automation techniques, and we will be having a low yield of powder between 20 to 150 microns. Yes, we are getting 0 to 500 micron powder particle sizes, but the yielding capacity for 20 to 150 micron is very less. That is the major disadvantages of this water automation process, and this is mainly used for non-ferrous, non-reactive materials. That is what the ferrous based materials, all the stainless steel based materials we are using the water automation techniques. And for the gas automation, again we are getting in the same range of 0 to 500 microns. This is we are having very much suitable for the highly reactive materials. That is what the titanium, aluminum, super-based alloys are most suitable for the wide range of gas automation process. Here it will be used for the high amount of throughput and as well as the rate of the particle sizes, and very spherical powder particles we are going to get in this water machine, and satellites are present, but it is a very small ratios, and also will be having a wide range of particle size distributions, and here also the yielding is very low in the range of 20 to 150, and this is majorly used for nickel based alloys, copper based alloys, ferrous based titanium, and as well as aluminum and cobalt chromium alloys and all. We are using gas automation process. And for the plasma automations, the range has come down. The particle size distribution range has come down from 0 to 500 micron to 0 to 200 microns. Here we are getting extremely spherical powder particles, and the major thing is it requires a feedstock in the form of a wire or in the form of a powders. We can use water atomized powder particles or gas atomized powder particles as a feedstock for our plasma automation process, or also we can use your welding filaments. The wire spools also can be used as a feedstock for your plasma automation process, and this is majorly used for our titanium alloys, because we need highly controlled atmospheric conditions for titanium. That's why we are using plasma automation is the very much suitable process for the titanium powders. And another one is plasma rotating electro automations. There we are getting still further decrease in the particle size distributions. 0 to 100 microns we can get high purity, highly spherical powder particles, we can get it, but the powder production is very very low. That is what low productivity and high cost, it will be used for titanium exotics. And for the centrifugal automation, the range has gone 0 to 600 and wide range of particle size with narrow particle size distributions. The size of distribution is very very narrow, and we are getting wide range of particles, and difficult to make extremely for the fine powder particles unless very high speed can be achieved. That is what how much your disk rotation, the centrifugal disk rotation, based on that we can able to control the size distributions. That is the major difficulties is there. To get the fine powder particles, we need to think of how much the particle centrifugal rotation of your disk, based on that we can able to control or achieve your fine powder particles. And the extremely using for the zinc alkaline batteries powder particles are pastes and all, and as well as the titanium and steel shards. For this purpose we are using centrifugal automation process. And the another one I told you, the hydration and dehydration process, we are getting 45 to 500 micron size of particle size distributions, and as well as it is of low cost of option. To get it into a very very minimal cost, we can get low cost, and will be having irregular powder particles, and is having high interstitial content of hydrogen or the oxygen content, because it is name itself defined as hydration and dehydration. Because of that, the hydration and dehydration process contaminated with the hydrogen or the oxygen contaminations. This is limited to metals which are more brittle in nature, and especially we can use for titanium also. That is what with respect to the powder manufacturing and its advantages and its uses for the EM processes. And if you see what is the key point variables for this powders and as well as techniques, will that could be used for their measurements. What are all the key variables means? The major key variables, the shape, morphology of your powder particles, whether it is spherical or non-spherical or it is irregular powder particle. That is what the shape will going to give us the whether it is spherical or not. Then how do we justify, how do we characterize this whether it is spherical or not? Means one way we can go with optical microscope, or we can analyze with the scanning electron microscope. That is what the assessment techniques will give us. We can able to assess the morphology of the powder particles by SEM and optical. And if you want to understand the size distributions, how do we analyze the size distribution or the particle size distributions? Means how do we sort out these powder particles? By your sieving process, different kinds of the sieves we can use to sort out this powder particle, either by mechanical sieving or by laser diffraction or by optical microscopy. In mechanical sieving, we can just segregate the powder particle sizes, but we cannot say what is the distribution. Is that how much D10 powder particles, D50 powder particles or D90 powder particles? Means 10 diameter particle how much distribution, or 50 diameter how much, or 100 micron how much. that we cannot able to segregate in your mechanical sieving. Just you can bifurcate the powder particles by mechanical segregation. But if you use that small quantity of powders for your laser diffraction or optical microscopy, we can say how it is distributed. That is what distribution of powder particles. And the particle porosity. Can we able to identify particle porosity? Powders are manufactured by water or gas automation. If powder is having a porosity, how can we analyze? How can we characterize it? By NDT techniques, or by the X-ray CT chromography, or by the optical microscopy. Optical microscopy or with SEMs only if it is having a surface porosity. If porosity inside your powder particles, then we need to go with a non-destructive testing only. Okay, that is what X-ray CT is the best way to analyze the porosity inside the powder particles. Okay, and the another, these are all the particulate properties, and the other one is the bulk properties. Bulk property is the density, flowability, cohesiveness, and as well as the surface area and the chemical composition. These are all the bulk properties of your powder particles, because these key variables are very much important in the additive manufacturing. If you are having less operant density or low flowability or low cohesiveness, then your chemical composition is changing, then it will be affecting your quality of powder part which is manufactured by additive manufacturing. Then all these things, how do we analyze? See, one by one we can go through that. This is what the powder particles, hydration and dehydration process, plasma automation, gas atomized, and plasma rotating electroautomation. If you see highly spherical powder particles, we are going to get it in plasma automation, plasma rotating electroautomation. In plasma automation, the another challenge is very fine powder particles or spherical powder particles that has to be bifurcated. But in plasma rotating electroautomation, we are getting highly spherical powder particles of required distribution sizes. That is what we can get it in the plasma rotating electroautomation process. But if you see this size, one is from Trueform or from the Praxair or from anyone, we need to control the melting, and then we need to understand the morphology and what is the solidification rate, how much level of your impurity, whether it may be the titanium oxygen contamination or maybe the nitrogen contamination. Any powders if you buy from the suppliers, we need to think of all these properties, flowable properties, distribution sizes, how much oxygen contamination and nitrogen contamination. It should be less than this, the 300 or 500 ppm in your contamination of the powder particles. Because if you do not think of these things, then ultimately you cannot able to justify the defects or the low properties in your mechanical caused by your powders or by your process conditions. That is why we need to buy a highly qualifiable powders by analyzing all these process conditions or the characterization aspects. If you see, I told you powder characterization can be done by particle size distribution, the impurity with ONH or the CS, or with tap density, alflometers, FT4, granodrum. With microstructure we can do with SEM or mechanical etching or optical microscopes and all, or with your confocal microscopes and all. And property measurements, that is what the hardness, tensile, high cycle fatigue or profile photometry or indentation or picrometry or Archimedes, all these are all the properties. And even we can go with the heat treatment aspects. We are using all these techniques to qualify our powder particles. Even we can analyze the hardness properties of your powders. Means those are all very much important, the morphology and characterization of the powders and all. And if you see the particle shape and shape factor, will that majorly influence your characteristics? Because we cannot quantify, because if you buy 10 kg or 50 kg of powders, we need to test only one lot of powders. We will just take the 100 gram of powders just to analyze these characteristics, flowable properties, particle size distributions. We cannot take all the 10 kg of powders to analyze it, Are we ensure that this entire 10 kg of powder particles going to behave same powder properties? Then how do we analyze these powder particles? Because we need to think of how much quantity of powder particles we are taking from the surface or from the middle or from the low. Because if you take the quantification analysis, we need to take from one lot maybe producing 10 ton. In that 10 ton, from all the aspects they have to take the powders and they have to measure. Then they can able to see for this lot this is what the characteristics. That is why we need to analyze all the shape and as well as its shape factors. Usually it will be described by the ratio and the shape factors, the aspect ratio and the shape factor. And aspect ratio is the ratio of the largest dimension to the smallest dimensions, and ratio ranges from spherical to the flake. And that shape factor is also called as a shape index. We are expecting very spherical powder particles. That will give us how do we measure the ratio of the surface area with respect to the volume of your powder particles. And the volume is normalized by spherical powder particles with respect to the equivalent volume. Will that shape factors of the flake is higher than the spherical powder particles. All these are all relating our flowability aspects. If you see the flowability, as I am telling, when the metal powders are being filled into your die, it should be easily flowed and as well as compacted. That is what gives us flow. Compressibility means when you are applying load onto that the poured powder into a container, how much extent it can able to compressible. And density, when we come to the density, because bulk density is different, theoretical density is different, apparent density is different, then as well as grain density is different. Then how do we qualify the density of your powder particles? Because if you take titanium density is 4.5, will that powders will also having the 4.5 density? Then how do we measure the density of your powder particles? Then density we are going to measure by using different things. That is what the flowable properties, grain density, apparent density and as well as packing density. But when you think of this characterization or the analysis of your powder particles, especially which is required for your additive manufacturing 45 to 110 or 106 or 15 to 45 or 5 to 45 microns with respect to the depending on EM processes, we need to characterize these things. But as I told, by SEM we can able to analyze the morphology of your powder particles. But if that powder particles microstructure or porosity, we need to analyze only by the mechanical aspects or by your using a X-ray CT tomography and all. But the cheapest method is we can put that powder particle in the mounting and we can do polishing to reveal this kind of a structure, and we can use this polished single individual powder particles under the microscope, optical or by SEM, can able to reveal the shape or any porosities are there or not. But what is the problem? If you see that sphericity is good, but still we are having roughly embedded powder particles or epoxy on the surface area of the powder particles. And sometimes what happens, these powder particles are not easily able to absorb by your electrons. That is why we are doing some kind of a coating. That is what sputtering we do, gold sputtering or any conductive sputtering we can use for coating of your powder particles, and then we can observe in our SEM, can able to see the powder particle morphology and all. But if you see, we have done some kind of a electroplating onto this the nickel powder particles with a tin coating, and just to reveal that how the shape and morphology. If you see that backscattered image and as well as secondary image will gives us the microstructure, how sphericity of your powder particles, and in the cross section does it having any kind of porosity or not. This is the simplest way of analyzing the powder particles. If you coat this electroplating with nickel, with tungsten and all, you can able to see the sphericity and as well as improving approach of particle size analysis. If you see these powder particles and as well as these powder particles, both are same powder particles, you have done coating with the nickel plating to improve its sphericity to analyze in your optical microscope. That is, with after mechanical polishing you can get more the edges and improved approach for our particle surface measurements. And if you see, this is what the porosity, which you can easily observe in your scanning electron microscope. But do we know this porosity is only surface level or does it having any volume? But in scanning electron microscope we can able to see only the porosity is visible in the surface. How much depth, what is the volume, we do not know. For those things we need to go with the X-ray, CT tomography only to understand the volume aspect of your porosities. Okay, this is what need to understand how much volume. If you see, this is what the porosity in your SEM, but in this one we are not seeing any porosity, only at these locations and as well at these locations. This is what in the SEM we can able to observe, but in the CT we can able to get the volumetric porosity of your individual powder particles. This is what I am telling with respect to only single powder particles. If you take the small quantity of 5 gram or 10 gram of powder particles, undergo with CT scan data, then you can able to get how much volume of your porosity existing in your individual powder particles. Because these are all very very important aspects when we use these powders in your IT manufacturing. Because when we have cracks, when we have porosity, lack of fusions, we need to understand this is caused by our process induced or porosity induced or powder induced, or it may be a lack of fusions. Because these challenges are going to be taken place when we are buying a very very highly qualitative powders. Need to understand these things. And if you see, some of the researchers have worked on this, the pure original powder particles and reused powder particles. If you see, this is the pure powder particles and how the microstructure with Inconel, titanium, aluminum or the scamalloy and all, and this is what the reused powders. What will be the problems? One is with respect to the change in the morphology of the powder particles. The surface remelting has taken place. If you see, this is what the surface remelting in all the aluminum or in the titanium powder particles, because titanium is highly oxidizing, it may contaminate the oxygen and it may be agglomerated. See, when we say the agglomerated, the surrounded powder particles are sticking onto the surface of the single powder particles. These called agglomerated powder particles, which cannot be used for our AM process, because it will be obstacle for the flowability and as well as packing factor. Then how do we break these agglomerated powder particles? Again we need to go with sieving deagglomeration technique to break these powder particles. Again we can re-sieve and go with some kind of a automation techniques or mechanical process to break these powder particles. Again it can be used for our additive manufacturing process. And that particle shape, that is what the aspect ratio with respect to shape, and the shape factors and the size distributions. As I told, the size distribution we can able to analyze in the particle size distribution with laser interferometry or with optical microscopes. With that, even with optical, we need to go with some kind of image processing analysis. That is what with the image processing we can able to see with different color coding, we can able to get what is the sizes, what color powder particles are there. With that we can able to plot the size distributions. This is with the simple image techniques, or even you can write simple MATLAB coding, we can able to analyze this kind of morphology with the particle size distributions and all. And even the standard techniques are there, particle size distribution techniques with the laser interferometry, we can able to get these kind of the normal distribution curve as well as skewed with left or right with the cumulative distributions. When we say this kind of distribution, your powder particles are distributed in one way, right side skewed or left side skewed, means we are having more amount of the powder particles above 50 microns. That is what the right skewness and the left skewness. But we require for additive manufacturing, we should have the cumulative distribution of the powder particles as a normal distributions. This is what we need to understand and we need to analyze for our additive manufacturing aspects. And if you see that powder particles, if this is the case, this is what used with X-ray instruments with laser interferometry. They have got these kind of particle sizes. Will that powder particles are sufficient for additive manufacturing, either PBF or for the DED process? We can use these kind of powder particles, but here the more amount of powder particles, the distribution or the frequency is 0 to 20, right. If you see that 20 to 100 microns, the frequency or the fraction of powder particles are very less, means we can use. Then what happens, the packing factor, packing ratio is going to change. Then we may expect so much of porosity or voids in the fabricated part or the printed part in your additive manufacturing. That is what we need to use. We need to have a high amount of packing factors. We are expecting to 1 at least 0.9 or 0.99 or 98, that much packing factors we are expecting with the normal distribution of your powder particles. The another aspect is, as I told, reused powders, what happens? One is agglomeration, one is contamination, and the oxidation. If you use titanium powder particles, original powder particles is like this, and if you are used powder particles, it is contaminated surface oxidation. This is with mapping, with the electro dispersive mapping, you can able to analyze EDS to get this kind of oxygen contamination. Like this, each individual particles, if it is contaminated with oxygen, then it is going to have a surface titanium oxide. To break that titanium surface oxide, we have to use more amount of the melting energy, more than the what it is required for titanium. Then we are going to use creating the process induced porosities, because we are melting, over melting the titanium powder particles. To break your titanium oxide, it will create your porosity by the process induced. That is one kind of the problem we are going to arise. Then another aspect is the cohesive strength. How do we analyze this cohesive strength? Because the powder particles, will it easily flow or will not? If you are using a alflometers like this, different kind of alflometers are there. With this alflometers, based on the ASTM standard 214 and as well as with respect to the 213 standards and 417 standards, we are analyzing how powders are flowing. We are taking 50 gram of powders based on the standards, and with this conical funnel of 30-degree inclination with the hole diameter of 2.5 mm or with respect to the hole diameter of 5.4 mm. And we are using this kind of Carney flow for our aluminum powders, which is not easily flowing aluminum powders. Those powders which are easily flowing, we are using a alflometers. With these things, we can able to analyze how your cohesiveness of your powder particles. Means when you use these kind of flowable measurement equipments, if you are forming these kind of cohesive arc, then if you take small amount of powder particles in your PAM and compress it, if you release your PAM, will it be holding a same shape or not? If it is having a hold same shape of your PAM, how much your compressing load is applied, then your cohesive strength is low or high? It is very high. Then that kind of powder particles, if you are using, it will not flow easily, because it is attaining your more amount of cohesive strength. It should fall easily. Flowable means it should not retain the same shape when you are applying load onto it. That is what easily if you are flowing, it may create some kind of rat hole also, because these two kind of powder particles are not suitable for our additive manufacturing. For these two powder particles, we need to apply some kind of a load or pressure onto the flow of powder particles. That will create your this kind of rat hole or cohesive circular arc in your the outlets. If you are using these kind of powder particles, then you are end up with a defects in your part fabrications because of these properties. Then what are the other factors which are affecting the apparent density? Then how do we measure this apparent density? Apparent density is with respect to the mass by volume. That is what we are using. Then the mass of the powder particle density which is holding in your cup, that is what in the 50 gram, and how much volume of density of your cup with respect to the alflometer, it will give us apparent density of the powder particle, which was measured by your ASTM standard 212 standard. Okay, this will give us how much apparent density of your powder particles. And also we need to make sure will that powders is a contaminated or oxidized, or we are applying any tapping or vibrations. That will give us how much amount of the moisture contamination, that is what the humidity, then it will lower the density. Means we need to understand all these aspects, as professor already told, because in different area we are having different moisture contaminations. If you go to NIT Surathkal in the seashore, we will be having more amount of moisture content. Even though you are packed in a proper manner, vacuumized or sealed in containers, it will be contaminated with moisture. Such kind of powders will be definitely having a low flowability. Then we need to preheat, then to make it remove the moisture contamination, to use that powder particle for our AM process. Okay, but in dry areas we are not required such kind of moisture removal and all. And the particle size distribution, if you see the atomized powder particles, the average particle also going to affect your apparent density. Means if you are thinking that the size of powder particles is 5.8 to 18, then if you see here the apparent density is changing with respect to your particle sizes. 5.8 your apparent density is 0.62, then if your size of particle is 18, then your apparent density is 1.09. Means the size is relating to your apparent density with respect to all kind of your powder particles. And then how do we measure this true density? The true density of your powder particles we are measuring with these kind of a picometers. That is what with general techniques we are using with the flowable of your gas, and then we are containing with the reference volume of your powders, and with the sample holders how much powder particles are flowing from one control valve to another control valve, and where it is collection is taking place. With this kind of picometer you can able to get true density of your powder particles to measure the true particle densities. And this is what the Hall flow meters which we are using generally for the all flowable powder particles. Which are not flowable, we are using Carney flow meters. And if you see the spherical, irregular and flake. If powder particles are very spherical, its apparent density is 4.5 and its tap density is 5.3. How do we define this apparent density and tap density? Why we are having variations in these things? If it is irregular, 2.3, 3.14, and the flake 0.4 and 0.7. Why we are having these changes? The apparent density, how do we measure? We know with respect to the mass of powder particles, that is what 50 gram, and volume of your container, how much powder particles it is contained, mass by volume. Then why the tap density is higher than the apparent density? Because we are applying pressure, tapping onto your powder particles, then it will compact more, then it will voids are going to be very less. We are compacting more amount to remove the voids. That is what applying pressure, it will increase the density of your particles. That will give higher density than in all the spherical, irregular or the flake like structures. If you are having a flake like structures, the apparent density is low because it will create more amount of voids, more amount of empty spaces. That is going to have the less apparent density and all, comparing with your spherical powder particles. That is how you can think of the apparent density with respect to size distribution and as well as tap density. Tap density will give us increasing the density of the powder particles. And if you see now we are coming to the sustainability. Till now we talked about characterization, powder manufacturing, how do we qualify the powders for IT manufacturing aspects. Then it comes to the recycling characteristics. That recycling will going to affect the size, roughness, surface oxidation, and as well as moisture contamination and agglomeration. All these properties are going to affect your flowability and good packing factors or the packing density. Okay. And if you see that powder degradation also will takes place. If you keep, you cannot store the powder particles like that, because if you take the powder particles and keep it for 5 years, and again if you use same powder particles for additive manufacturing, then what will be the problem? Can you use that kind of a storage of powder particles? Yes, for ferrous based materials, and if it is a non-ferrous materials, we cannot able to store such like that, because it will contaminate, it will oxidize, or it may be impurity or foreign particles may be contaminated, and even during transportation it may be contaminated. That's why we need to think of how degradation, will that deformation or oxidation or dealloying or sintering or wear or fragmentation or oxide deposition, because once we use the powder particles, all these come across in a picture. Your powder particles, once we use for printing inside even our vacuum chamber or in the organ atmosphere, it will be come across with all these process parameters, because your molten pool is surrounded with the powder particles. That powder particles are going to affected by heating or by the molten pool bath or by the energy sources or by the fluid dynamics interactions. Because of these things, your reusing of powder particles should be very, very careful. Some of the studies have undergone this reusing of the powder particles. How much extent we can able to reuse? Even we have studied lot of aspects, in what extent we can reuse the powder particles, either titanium or stainless steel or some other stainless steel based materials, martensitic or austenitic materials and all. And if you see that this is the highly spherical powder particles, fractured powder particles, deformed powder particles, irregular, satellites, and as well as melted. There is a different size, different morphology of powder particles, right? In these things, if you see, the original powder particles is E, right? Because that does not fracture, does not deform, does not having any sphericity, right? If you use these kind of powder particles, or if you are using some kind of recycled powder particles, what is the volume fraction? If you see the powder size and as well as the distribution, recycled one and the original powder, red one is original and the black one is the recycled one, means the size distribution is changed. Why the size distribution is changed? Because it may be agglomerated or it may be contaminated these kind of satellites, or it may be fractured or it may be deformed. Because of all these things, your recycled powder particles changing the distribution sizes. Okay, and if you see, this is what the recycled powders, this is what the original powder particles, because so much of satellites are there, so much of agglomerated particles are there. If I use these kind of powder particles, then what is the things, what is the porosities, what is the mechanical properties we are going to come across? If you see that the powder particles, recycled powder particles and the original powder particles, the porosity diameters inside our particles, the pore diameter is very, very high, the count number is very high in the recycled one, but in the original one, the porosity and the pore diameter and the count is very, very less and all, because this will also going to create and the oxygen contamination. If you see the original powder 200 to 250 ppm, but in the used powder almost 350 ppm level, the oxygen contamination is increasing. If you use these kind of powder particles, then we are come across with the poor mechanical properties. And if you see, if I use these kind of the reused powder particles, what are all defects we are going to come across? Either porosity, distortion, or roughness, or cracks, or maybe inclusions, or delaminations, or maybe straining, going to create all these poor mechanical properties and more amount of residual stresses in the printed part and all. That's why we need to think of how many number of reuse cycles to get the repeatability in the part printing. One of the study people have done to reused powder particles and as well as the original powder particles with the stainless steel materials, and they have come across with astral also, if you see, this is the original printed powder particles and with the reused powder particles. If you see, the porosity level is 0.4 percentage, and if they use reused powder particles, they end up with 1.47 percentage. This is what with the X-ray CT data and with the optical micrograph. With the optical micrograph, we cannot see much differences. We can see the melt pool, we can see the porosities at different locations, but when you see that porosity in the volumetric, you can able to come to know the porosity level is increased in the reused powder particles. That is what, if you see, the volume of porosity is increasing with respect to the defect diameters. And if I check this, the volumetric porosity, if you see that recycled powder volumetric porosity is very, very high. And if they use the mechanical properties of that recycled powder, if you see that original powder will have the more amount of ductility properties, elongation properties, then the recycled one is poor elongation properties, and it is matched with your more or less same of the yield strength and the tensile strength. This is because the powder particles are oxidized, and then if you see that the fractographic images of that powder particles, more amount of the cracks and the delaminations or voids can be observed in the recycled powder particles comparing with the original powder particles. This is the causes for your decreasing mechanical properties as well as ductility of the part and all. But if you are not knowing who is the supplier for our powders, then we are not going to compare our the quality of the printed parts with respect to the certifications and all. That is why we have to make sure the powder particle should be original and has to be highly qualified for AM. Okay. The another part people have done with the 17.4 pH and all. As I told, the properties are going to affect porosity, distortion, and as well as straining and delaminations. If you see here, what happened here, the original and as well as the reused powder, it has got deformed. The part has got deformed because they are used the reused powder, and that reused powder are going to create deformation in the printed part because of the more amount of the straining is taken place in the printing. Because we are supplying more amount of energy, either maybe because of oxidation or to melt or to minimize the porosity levels and all. Because of that, it is going to create deformation in the parts and all. If you they have analyzed in depth to understand why that deformation, what kind of defects are going to come across in the reused powder particles. If you see, they have analyzed with the TEM, then that oxide inclusions in each layer they can able to observe. If you see, this is the one layer, multiple layers, in each layer they can able to see and understand the oxide inclusions in each layers. Because of this oxide inclusion, you can able to end up with the difficulties or different oxidant contaminations in your printed parts. Is what oxide inclusions they have understand with the mapping, with the EDS mapping. You see these dark patches of all the oxide inclusions which are come across in the printed parts. This will give a poor mechanical properties in the additive manufactured parts, and also create these kind of the porosity and all. Thus is caused for your poor ductility. If you are having more amount of porosity, then automatically the ductility will be very low. Because of that, you can able to see, understand. Then now if you think of the sustainability impact drivers for metal additive manufacturing, we are talked how much reuse of your powder particles, 4 times or 10 times or 15 times. If I use 4 times, what will happen? If I use 2 times, or if I use even after saving, will be directly you are using recycled powders for additive manufacturing, either LDD or PBF process. Yes, we can use even up to 4 times, but we are end up with these kind of problems, either the inclusions or variations in the ductility properties or the strength properties. But if you think of the wastage in the DD process or in the PBF process, if you see here, the 60% wastage will be there. But when you think of these things with respect to binder jet or EVM or with the SLM solution or with the PBF process, if you see the how much amount of the energy efficiently requirement with respect to the process rate. means the electricity or the energy which is required 8.3 e to the power of 7 joules per kg is required in the bind jet process, 6.1 in SLM or the PBF process or in the DMNS system. In the EBM we are using less energy requirement, that is what 1.1, more than that the SLM and the bind jetting we are using. Means this is how we need to understand how much the energy requirement, that is what the cumulative energy demand is required with respect to the different processes and all. That is what the power or the energy intensity or the production rate of our powder comparing with your conventional manufacturing process. Is that really the suitable for our the application aspects and all. The one way how we can make it sustainable means how much quantity of your powder particles using, how much energy we are using, and what is the carbon dioxide emission, and how much amount of argon gas we are using comparing with your conventional manufacturing process. We need to quantify how much topologically we are redesign, means if part is complex, then we need to go for multiple manufacturing process in conventional, multiple scenarios, multiple assemblies, welding or fixture or with rivet joints or with assemblies are required. But in AM we can go with a single process, but how much energy is required in terms of gas or in terms of powder, in terms of machine, in terms of post processing and all, we need to calculate, and then we can think of how sustainable it is. That's what we need to know. Data is available in this sustainability aspects, but we need to think of how we can able to quantify in terms of sustainability aspects and all. That's what we need to think of, whether we are using recycled powders or whether we are using original powder particles and all. That's what with 4K and 6K additive solutions, they have started developing powder particles with recycling. Means they are collecting all the powders from the users, those are the users, maybe industries or from the academia. They are collecting the powder particles, used powder particles, even though after they are used 2 times or 4 times, rest out powder particles is contaminated, is oxidized. Those powder particles they are collecting to the industry, then they do receiving, then they go for some kind of the removing of impurities, then they are producing the powders again like a original powder particles. If you are using like these kind of powder particles, then it is more sustainable comparing with your conventional aspects. That's why we need to think of, even people are doing with your some of the scraps, whether we are using machined materials, even 6K is 6K additive solution, they are also using machined scrapping. By turning or milling, if you do the machining of any material, they will collect all these chips and then they will collect in terms of a tons, then they use that all the chips to be contaminated, because you are using so much of coolants, it may be contaminated, oxidized because of the heat affecting during machining and all. Then we have to clean all these aspects by impurities and removing all these oxidations and contaminations, then they will melt it again, then they will produce the powders. Instead of going for the original powder manufacturing, you are using the scrap from the conventional, that can be used for making the powders, that is more sustainable than the original powders usage in the additive manufacturing. Also we need to think of how the powders are produced, but will that giving a same quality aspects in terms of the reproducibility or the mechanical properties and all. That is also we need to think of in terms of sustainability aspects. 6K has started even the support structures, because when we print metal parts and in PBF process or in DD process, we are providing so much of support structures. Wherever we are having overhanging structures, we need to provide support structures. Then what is the waste of these support structures? Because support structures we are providing in different simple designs and all, just to hold that overhanging which is possible for the painting. Even in the EBM, so much of the stuck powders or the agglomerate powder particles will be there. These are all like acts as support structures. All these powder particles can be a raw material for your powder productions or the chips. All these the rejuvenated powder particles. agglomerated powder particles, can make use of the premium the powder particles with the plasma automation or with the vacuum induction automation process. With that, 6K has developed these kind of support structures or this kind of unused powder particles or part which is already broken or it may be deformed during printing, it may be failed. All these they have done collection from the industries as well as from the academia to produce the powder particles. That is what the failed powder particles, failed builds, support structures or condensates, or it may be primary ingots, or it may be reuse of partially melted powder particles, or the machine turnings, or the end life of the powder particles. All these things they can collect it to make these kind of the premium powders by the plasma automation process and all. That is how they can use these kind of powder manufacturing. If you see, initial process is what? If you are using a chips and all, these kind of turning chips or milling chips and all, then we can use these kind of simple chips by the mechanical milling, ball milling process. We can use to produce these kind of the powder particles as a, this is not spherical but somewhat nearer spherical. Such kind of powder particles we can make use by your ball milling process. Chips are converted into a powder particles by mechanical attrition. Even mechanical attrition we can use, tumbler milling we can use, this kind of ball milling we can use to produce this. These raw materials can be used as a input for your plasma automation or for the gas automation techniques. That is why we can use. This is what the methodology to clean and prepare your machining chips, because we cannot use directly these chips for producing, because it may be contaminated with your coolants or it may be oxidation or it may be some other impurities and all. That is why we need to clean that powder particles. For that we have to follow these processing stages after the machining chips and all. Whatever the coolant impurities we need to clean with water with other solvent solutions, and then what are the detergents or ethanols or acetones, isopropylene alcohols we can use to clean it, or it may be worn out from the tool contaminations. Tool may also worn out contaminated in the chips and all, that also has to be cleaned, and then we have to use that recycled one for making the powders by the mechanical processing. This is what the flow chart we need to follow for making the powders by the machining chips and all. And once if you are following all those aspects, we are using that powder agglomerated powder particles to make the very spherical powder particles with the vacuum induction automation or plasma automation process. That is what, if you see the regenerated nickel powders, 6K additive solutions have proved to sustainability in these powders. Means worldwide they are the leading manufacturers nowadays. The used powders they are buying and they are selling in a minimal cost with this kind of the powders, because this will be very equivalent to your original powder particles. That is what, highly spherical powder particles, and they are more flowable properties, very good compaction, very good apparent density, and all the aspects are required in these powders. That is possible by the automation techniques. With the rejuvenation we can able to do it. And even if you see these kind of chips, recycled scraps, machining or 3D support structures or scrap from the 3D parts are used, that can be used by the low cost mechanical pre-alloying or mechanical processing. Then we can use that low parts or with different kind of processes, EBM or PBF or LDD or with binder jetting. All these things can be used for making a high quality powders by adapting the sustainable sources. These are all the sources for making the powders instead of using a original powders from the ingots and all. And if you see that quality, then how do we assure that these kind of powder particles are quality assured? Then that 6K solutions has maintained the quality aspects in terms of characterizing all the properties, start from first to flowability, morphology, sphericity, and then how they can able to clean it and how they can able to engineer into a feedstock, and then how they can able to sphericize to produce the highly quality powder particles. Then they qualified that printed parts with the original powder particles to qualify repeatability in the original powders and the reused powders. This is how we can make use our sustainability aspects in our powder manufacturing. That is powders how we can use for our additives also. From this takeaway, if you see the summary of these aspects, we can adopt even nowadays the machine learning techniques, because we are producing the powders, but will that having some kind of the technological adaptment? We do not know how machine learning based techniques are efficient for framework in developing this automation things. None of the people have adapted this machine learning techniques for adoption of the powder automation. One can apply that kind of the machine learning techniques to powder manufacturing, powder productions and all. And another one is a use of real model with identifying the optimal production conditions while accounting for the real world constraints and all. Because we have lot of constraints in the powder manufacturing. That is what in situ monitoring, how we can improve the yielding effective or automation, because yielding is very low in your automation. How we can able to improve that yielding of your automation? That's one way I can think of. How improve the sustainability through the efficiency, gains and renewable energies and integration and scrap material utilization. We can reuse all the scrap materials instead of throwing into the environment. We can reuse all those things and we can use it for a raw material for the powder productions and all. And promote powder recycling as a key component for the circular economy. We have to promote in all the Asian or European sector recycling of these powder particles. Then we can able to use as a circular economy for our powder productions and all. And reduce the carbon emission and energy consumption through this coordination effort across this overall AM workflow. Then only we can able to minimize the environmental impact of your powders or the additive manufacturing on the society. That is what we can minimize gas house emission effect and all. And also recognize the critical importance of the powder sustainability in terms of the powder bed fusion process. Because in powder bed we are almost 60% of powder wastage will be there. Because the entire build area we are not going to build, it is not a complete a solid block, it will be of depending on the structures, then support structures we have to provide, almost 60% wastage will be there. Then we need to think of how critically powder sustainability can be done in PBF aspects. And emphasizing the recycling, resources conservations as well as the fundamental achieving the sustainability in the additive manufacturing aspect. These are all the things we need to understand to apply our sustainability in our additive manufacturing process. But all these things cannot be applied, but there should be a trade off between the sustainability aspects and as well as additive manufacturing. Means even all the quality powders in terms of PBF process, what is the binder jet process, or with respect to multi-material additive manufacturing. Even multi-material it will be difficult. If you go with the copper or nickel based alloys, copper with stainless steel alloys, it will be contaminated copper as well as steel. Then again we have to separate out with the density aspects and as well as with the chemical aspects. Then it will be a more tedious process for sustainability aspects of such kind of functional grade materials, multi-materials. There is a trade-off between these sustainability and as well as with respect to the additive manufacturing aspects. Okay. With this I will conclude. If you have any doubts or clarifications, you can write to me or you can require, I can able to answer your queries.